Hi, hi guys, my name is Carlos Carral. Today I'm going to be discussing uh, a thing called Schedit, a little thing I wrote, specifically the underlying algorithm. I'm going to try to make this as less. I'm going to try to make this not as much as a lecture, but keep in mind it is a technical talk. So, what the hell is Schedit? Schedit is a scheduling web app. No, not that type of scheduling. I know it has a very specific meaning within the computer science discipline, and this is not that, but I don't really know how else to call it or the problem it solves. So I'm going to try to explain it in simple terms. Let's say you have a course sign-up deadline coming near, so your semester is about to begin, and you must sign up for a given number of subjects, each with many courses available, and you don't want to fall behind. So how do you take this long list of courses and effectively begin building your ideal schedule? Okay, so let's say I must take up calculus, algebra, geometry, computer science, and physics, and I have many options for each subject. So it will also be nice to have the choice of selecting a specific professor or a specific time for a given course. So how can I actually find a combination of these subjects that actually fits my needs? So enter Schedit, somewhat unassuming web app. What do I mean by unassuming? Well, this is it. So I'm going to try to show how it works. Let's say let's say I want to take up network architecture, compilers, and this let's say discrete mathematics, physics, programming 101, let's say network auditing. I have 6. Okay, I have selected 6 possible subjects. Actually, I'm going to select another one, digital systems. Now I have 7, but I actually want to sign up for 6, so I'm going to reduce the number of subjects I'm going to take up, and I'm going to generate all possible combinations. Okay, so this is the actual output, and please note that these are actual courses I could sign up for. I have many options. So it's very simple, and I can get it in PDF format, but I mean, it's okay. It gets the job done, but this is not what I'm here to talk about. I'm coming here to talk about the algorithm. A few things we have to know before digging into the actual algorithm. How do I represent a single subject? A specific course is going to be represented as a square matrix, specifically 48 by 7 square matrix. Then that is 48 half-hour blocks between midnight and midnight, actually, and any 7 days in a week. So let's say a class takes place on Monday, Wednesday, and Friday, from 12:30 to 1:30. A 1 is placed in its corresponding time blocks. So this is this is how we see it. And actually, this is how the algorithm sees it. The same data, just represented as a square matrix. Okay? So far, so good. Now, I actually need an operation to merge two single subjects, two single courses together. This is what I'm calling the merge operation. We're going to add two matrices, and for each element in each matrix, we're going to verify that the element is less than 1. So we have these two little matrices, and we're going to merge them. See? So every single element in the resulting matrix is 1, so it's okay. And this intuitively means that there is no overlapping between two courses. Okay? This was a successful merge. Now, this is an unsuccessful merge. So see that these two places are taken up. So when I add them, we have a 2 here and a 2 here. So this means that these two courses are not compatible. Which in reality it means that two classes take up the same time block. Make sense? So I'm going to talk a little about course sets. So a course set is a set of courses usually related by a common subject. So for example, intuitively, we would group all algebra courses into a single set named A, which would contain all courses for taking up algebra, right? A subject stack is what I call a single combination of different course sets. Please note the word combination in this context, because it has a specific meaning, and that is the order is not important. That is, it's not a permutation. Okay, bear with me. I know this might be a bit too math heavy, but okay. So for example, what do I mean by course stacks? Let's say this is the list of all my available subjects, and each one has its own courses. It could be one, it could be many. So the length of the list of all subjects is 5, but I have a desired stack size of 4. So what does that give me? It gives me multiple combinations of 4 subjects. So this stack size that I talked about earlier is actually this little number. See, that's effectively, that means how many subjects do I want to, how many classes do I want to take up on a given semester. So in this case, my selection was 6, right? Okay. So the input parameters for the algorithm I'm going to name G, which is defined as the global set of all available course sets grouped by subject. So this is the big list of available classes that we as students are given at the beginning of the inscription cycle. And K is going to be the total course set length to be fit into the final schedules. That is the stack length, that is the how many courses I'm going to take up on a given semester, right? Let's start with the actual algorithm, right? So we generate all possible combinations of length K, that is the stack length, over G into stacks. So we group all possible subject combinations. Remember, these are individual classes, individual courses, and each level in the stack is a subject. So as the earlier example, the stack length is of length 4, and we're going to generate all possible combinations of length 4 over G, right? Next, for each given stack, we're going to do the following. We're going to initialize an empty grid, that is an empty square matrix. We're going to select the first stack level, and we're going to merge them with the blank schedule. And this operation will always be successful, right? As it's an empty course, it's a blank square matrix, so the merge operation is always going to be successful. Now, the recursive step. So we're going to go depth first. This is actually a backtracking algorithm, I think. So first, if there are no more stack levels, we have successfully completed that path, and the resulting schedule will be added into the list of generated schedules. So this is the actual stopping condition for the recursive algorithm. Now, next, if this isn't the case, for each individual course, we're going to try to merge them into the blank schedule, and if successful, we're going to descend into the next stack level. And if the merge was unsuccessful, we're going to go over the next schedule at the current stack level. This might be a little too abstract for visualization, so I'm going to try to explain it visually. We start here, right? At the first stack level. We perform our first merge. We're going to descend a stack level, right? And for each, this is the recursive step, for each of these ones, we're going to try to merge them with the blank schedule, which is now not blank, right? So did this one fit? Does this one fit? No. This one, yes. This one could be successfully merged. We descend into the next stack level. This one fits, right? So we descend into the next stack level. Does this one fit? No. Does this one fit? No. So we completed a successful path. When we reach the end of the stack, we are said to have performed a successful path, right? From A to B to C to D. So we add this path into Q, right? So, and this is the generated schedule. Okay, so the output is going to be a resulting list of all possible schedules based on the initial course list and the desired schedule length. And this is a neat little detail. This algorithm has the option of adding what I call seeds. A seed is a specific course. Let's say I want to take up calculus with a teacher that is said to be very good. So I'm going to select that specific course as a seed, and now I'm going to generate all the possible courses I can with that specific class, right? Now this hasn't been implemented yet, but if desired, we could add an additional optimization step so that unproductive time blocks are minimized. That is the length. This length between this class and this class could be minimized, so there are no dead hours, right? Now this is a very specific problem, and the algorithm reflects that. But I don't think it could be used solely for that. I think it could also be used for planning schedule shifts. For planning employee shifts as a manager, or in general for spreading coverage of limited resources over time. So let's say I have I don't know, I have a couple of labs, and I want to schedule the appropriate hours so that every student can use them and nobody gets left behind. Right. So I know I said I was going to talk about the algorithm, but I want to talk a little bit about the implementation because I think it's neat. So this is a standalone web browser app brought to life by Rust and WebAssembly. And I like this specific detail because it operates completely on the client, and it was built using Rust, and using Rust allowed me to be more it allowed me to relax, knowing that this specific brute force algorithm, it's brute force but in an ordered way, I think, but that this specific brute force algorithm was being performed at least somewhat efficiently, and yeah, so the entire application is compiled. It's a Rust engine. It's compiled into WebAssembly and packed into a usable node package, which is then transpiled into just plain JavaScript and TypeScript, and yeah, it's quite nice. So actually, you will see this URL parameter, and this is actually the input where we enter the input for the web app. This specific file is a comma-separated file. So in theory, we could use the same web application for accessing any publicly hosted file. So yeah, that's it. I think it works well. I think it has saved many hours in my college. A lot of my friends have used it, and I have been pushing for more resources deployed for more resources pushed into this. So we're going to see. I think it has a lot of potential. It might not be the most technologically challenging thing I have done, but it solves a real problem, and I am proud of that. So yeah, I think I hope I made myself clear. This is actually accessible through my website. I'm going to post a link below so everyone can try it. Yeah. So thank you for watching.